So here are the quiz questions. Limit as x goes to 3 of, oh, well, that first one is, oh, x goes to 9. I was like, that seems wrong. Square root of x minus 3 over x minus 9. This one you could accomplish by factoring. Technically, the bottom factors is x minus, or the square root of x minus 3 times the square root of x plus 3. This is one way you could do this problem. It's not the intention, but it would work. But really, the idea here is to use Lupital's rule. You've got a 0 over 0, right? 3 minus 3, 9 minus 9. Taking the derivative of the top, the derivative of the square root of x is 1/2 x to the minus 1/2. The derivative of minus 3 is 0. The derivative of x is 1, the derivative of minus 9 is 0. So there's our expression. And, oops, come on. Sorry, I'm trying to pull in. And then we can just, or I guess we should plug in 9. And I will say, every time you apply Lupital's rule, you should always check to see, can you plug in the number now? And we can. You might want to rewrite it to make it easier to see. This is the limit as x approaches 9 of 1/2, or I should say 1 over 2 square roots of x. And then we can plug in 9. Get 1 over 2 times the square root of 9, which is 3. So you get 1/6. That's it. Let's look at the next one. Again, these are the questions from the quiz I gave you guys over the weekend. So here's 2. The limit is x approaches 0. The tangent of x minus x over x minus sine of x. So if we plug in 0, we get a 0 over 0 form. Right? We always have to check. Is it one of the forms I can use Lupital for 1? Tangent of 0 is 0, minus 0 is 0, and 0 minus sine of 0 is also 0. So I'm going to use Lupital's rule. The limit as x goes to 0. The derivative of tangent is secant squared. Derivative of x is 1. Derivative of x is 1. Derivative of minus sine x is minus cosine of x. And now if we try plugging in 0 again, we get 0 over 0 again. Secant of 0 is 1. 1 minus 1 is 0. 1 minus cosine of 0 is also 1 minus 1, which is 0. So we use Lupital's rule again. I will point out you could use a trig identity here. It's probably not necessary. The trig identity I'm referring to is the fact that secant squared minus 1 is equal to tangent squared. That is a trig identity. But let's use Lupital's rule one more time. So we have to be a little extra careful here. The derivative of secant squared, or some stuff squared, is 2 times my stuff to the first power times the derivative of my stuff. And the derivative of secant of x is secant of x tangent of x. All over, let's see, 1 minus cosine, the derivative is 0 plus sine of x. Now, if you look at this, we still have a 0 over 0 form. And it doesn't feel good. I don't really want to have a 0 over 0 form here. It's not that it doesn't feel good, it's that if I try to use Lupital's rule one more time, it's going to be painful. Derivative of sine is fine. The derivative of secant times tangent is going to be kind of hideous. This is where we should take the alternate option of simplifying if possible. So I noticed that tangent is sine over cosine. In fact, I can write this whole thing as the limit as x goes to 0 of, well, secant is 1 over cosine, so I've got 2 times 1 over cosine times another 1 over cosine times tangent, which is sine over cosine, times 1 over sine. And look, the sines cancel out. And then if I take the limit as x goes to 0, I get 2 times 1 times 1 times, that's it. 2 times 1 times 1. I mean, times 1. Doesn't matter. But you get, right, you get 2 times 1 over 1 times 1 over 1 times 1 over 1 times 1 over 1. So sometimes, even though you could use Lupital's rule here, it's really going to be quite hideous to take the derivative of the numerator. So sometimes, a lot of the time, it actually makes sense to try and simplify your expression instead of using Lupital's rule. All right. I will point out, just because I think it's worth pointing out, it probably would have been slightly easier here to actually do the trig identity I mentioned if we had instead written this. So again, I'll remind you that my favorite trig identity, 1 plus tangent squared of x equals secant squared of x. Or as I was told by a student, I tan and get sexy. I tan and get sexy. Can't forget it. It's impossible to forget. So if I subtract 1, secant squared x minus 1 is equal to tangent squared x. So I could have instead rewritten this as the limit as x goes to 0 of tangent squared x over 1 minus cosine x. And then use Lupital's rule from there. It's still going to be kind of a pain. Right, the derivative of tangent is going to be, let's see, the derivative of tangent is 2 times tangent times the derivative of tangent, which is secant squared. You know what? It actually, so this is kind of funny. I thought it was going to be better. It's not. In fact, not only is it not better, it's literally not any different. The derivative of tangent squared ends up being the same as the derivative of secant squared, which I should have known if I had thought about it. So yeah, same work either way. Why should I have known that? Well, because if secant squared and tangent squared differ by a constant, like they differ by 1, then their derivatives should be the same. Right? Just like x to the 4th and x to the 4th plus 5. They differ by a constant, same derivative. Okay, enough of that. Let's do the other problems, which are slightly more interesting because they don't start off in a form where you automatically can just use Lupital's rule. So let's look at this one. Look at the limit as x goes to minus infinity of x cubed times e to the negative x. So this problem is a infinity, technically a negative infinity here, times, oh no, it's either the positive. I made a mistake. So if it was like this, we wouldn't have to use Lupital's rule because you'd have a negative infinity. And negative infinity cubed is negative infinity. And e to the negative infinity is e to the infinity, which is really, really large. And negative large number times a positive large number is a negative large number. But what I actually meant to ask was the limit as x goes to negative infinity of x cubed times e to the positive x. And now this is an indeterminate form. It is a negative infinity times a 0. And negative infinity times a 0, that's why it's called an indeterminate form. Right? We don't know what it could be. Just like a 0 over 0 could be 2. Or a 0 over 0 could be 1/6, right? It's indeterminate. That means it can be anything. Here, this 0 times negative infinity, we have to figure out what it's going to be. And the only way we can really handle this is to re-express it in a way where we can apply Lupital's rule. So we have to write it as a fraction. Now, there are two choices. Whenever you have a power of x and an e to the x, you almost always want to put the e to the x thing in the denominator. I'm going to write this as the limit as x goes to minus infinity of x cubed over 1 over e to the x. Let me go turn on the heat real quick because it's been hot in here. Yep. Okay. So, I'm going to use Lupital. So first of all, I can use Lupital's rule now because x cubed is going to negative infinity, and 1 over e to the x, well, e to the negative infinity is going to 0, and 1 over 0 is going to infinity. So this is blowing up to infinity. So I'm going to use Lupital's rule. I'm going to take the derivative of the top, which is fine. For the derivative of the bottom, I'd really rather rewrite that. I'd really rather write that as x cubed over, instead of 1 over e to the x, e to the negative x. I'd much rather express things in ways that are going to make them easier to differentiate. So then I'm going to use Lupital's rule. Again, noticing that I have a negative infinity over infinity, right? It's okay if the infinity types aren't the same. You can have a negative over a positive. So using L'Hopital's rule, let's see. The derivative of the top is 3x squared. The derivative of the bottom is negative e to the negative x. And now it looks like we have a positive infinity over a negative infinity. Still indeterminate. So we use L'Hopital's rule again. I think I might not have, should have worn a long sleeve shirt today. It's a little too warm in my office. So using L'Hopital's rule again, the derivative of the top is 6x. The derivative of negative e to the negative x is negative e to the negative x. So just e to the negative x. We still have an indeterminate form. It's still a negative infinity over infinity. So we do it one more time. One more time. And we get the limit as x goes to minus infinity. Derivative of the top is 6. Derivative of e to the negative x is negative e to the negative x. Whoops. Ooh, negative e to the negative x. And so we get 6 over something that's getting negatively infinitely large. That's going to go to 0. So in this case, it is 0. I really want to point out, and I'll do that with another example after this next one, that a 0 times the infinity can really be anything. It's not always going to be 0. This one happens to be 0. But right, again, you don't really have 0. You have something very small. It's multiplied by something very, very large. In this case, the small thing was getting smaller faster than the big thing was getting bigger. All right, let's look at the last one of these. Again, I'm going to emphasize here that whenever you're faced with a limit and you think you might want to use L'Hopital's rule, you have to be able to write it so that it looks like a 0 over 0 or an infinity over infinity. So let's look at this next one. And I'm not sure how you should talk about these. So I'm going to talk about this both ways. So I'm going to do the limit as x goes to 0 of 1 minus 2 over x to the x. And now some people like to write this the whole. So here's how you kind of start either way. I'm going to write this as the limit as x goes to 0 of e to the natural log of 1 minus 2 over x to the x. And I should point out, the reason I'm doing this is because I have an indeterminate form. This form here, this is a, except I think I actually, this is not an indeterminate form. I might have blown this one. That's all right, we can still look at it. But this one actually, so if you did the quiz, you might have been like, why would I have to use L'Hopital's rule here, James? Because I clearly don't. Let's check it out. Actually, this maybe I take it back. It is an indeterminate form, it's just weird. Usually, x would be going to infinity here, but we'll see that in a second. So what have I got? I've got 1 minus 2 over 0. That's going to some sort of infinity raised to the 0th power. Okay, that is still an indeterminate form, so I'm not totally off base here. Usually the people tackle things like this. I do have to make one adjustment though. I do have to be approaching 0 from the right here, I believe. Actually, no, from the left. Yeah. Sorry. I'm not actually sure what's going to happen here. That's okay. Sometimes I don't know what's going to happen. Yeah, that is going to happen. Let's take a look and see. So I'm not sure which way your guys' teachers have done it. Sometimes they just deal with this whole expression the whole way, or sometimes they're just going to say, I just want to look at this, and then I'm going to look at the limit of that, and say that my answer is going to be e to the whatever I get for that limit. Either way of doing it is fine. Some people like doing it this way because it's kind of less writing stuff down. So let's look at the limit as x goes to 0 from the left of 1 minus 2 over x. Sorry, the natural log of 1 minus 2 over x to the x. And the reason we have to be approaching 0 from the left is so that this part is negative, so that this whole part is positive. Otherwise, you couldn't take the natural log of it. All right, so when you've got this thing here, this natural log of some stuff to a power, the whole reason we took the natural log over here as e to the natural log was so that we could bring down the power. And we're always going to bring down the power. So we have an x times the natural log of 1 minus 2 over x. And then I'm going to bring down the x below as its reciprocal. This is going to equal the limit as x goes to 0 from the left of the natural log of 1 minus 2 over x over the reciprocal of x, which is 1 over x. This is always the process. When you have an exponential indeterminate form, you're always going to take the natural log of that thing and then bring down the power and then bring down the thing in front as its reciprocal. These steps always happen this way. And now I'm going to check to see that I actually have an indeterminate form. You will, but we should still check. This top part is going to infinity because the inside, so let's see, 2 over 0 is blowing up to negative infinity. 1 minus negative infinity is going to positive infinity, and the natural log of infinity is infinitely large. And 1 over 0 is going to an infinity. In this case, it's a negative infinity. My thing just beeped, but I don't see a person. Oh, there we go. All right, cool. So let's use Lupital's rule. I'm going to remind everybody off to the side here real quick that the derivative of 1 over x is the derivative of x to the minus 1, which is minus x to the minus 2, which is minus 1 over x squared. So the derivative of something over x is minus 1 over x squared times that something. Let's use Lupital's rule. The limit as x approaches 0 from the left. Let's see. So the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. The derivative of 1 minus 2 over x is going to be 0 minus the derivative of 2 over x. Well, the derivative of 1 over x is negative 1 over x squared. The derivative of 2 over x is negative 2 over x squared. This is going to be negative 2 over x squared. Or just 2 over x squared. Over the derivative of 1 over x is negative 1 over x squared. And what I would like everybody to get to see here is that these x squareds end up canceling out. I think you're good just to cancel them out right away, but if you don't like that, we can do a little bit of algebra. We can write this as the limit as x goes to 0 from the left of 1 over 1 minus 2 over x times 2 over x squared times x squared over negative 1. Then these cancel out, and you get the limit as x goes to 0 from the left of 2 times negative 1 is negative 2 over 1 minus 2 over x. Now this is where things are going to be a little different than I expected them to be. But let's take a look. So if I'm approaching 0 from the left, it means my denominator is very small and negative. So 2 over that denominator is very large and negative. And 1 minus that is very large and positive. 1 minus a negative infinity is a positive infinity. And then negative 2 over an infinitely large number is going to be small. And so my answer here is e to the 0, which is 1. Kind of funky. I do want to point out that I would like to show you guys what the question I actually wanted to ask was, because that was actually the more interesting question. So we're not going to repeat all this work because I'm really just about to do the same thing. The only thing I'm going to change is I'm going to write, actually, you know what? I am going to show this working, but I'm going to show kind of the other people do it because I think that's worthwhile. So let's look at this limit again, except let's look at the limit as x approaches infinity. That's slightly more interesting. So let's look at the limit as x goes to infinity of the same expression, 1 minus 2 over x to the x. Now, I will point out, when we do this, we're going to get all the way down to the same spot. We're going to have the limit as x goes to infinity of this same expression. But I am going to do it this other way, where I'm going to write the e part the whole way. So write this as the limit as x goes to infinity of e to the natural log of 1 minus 2 over x to the x. Now, the process is still the same. I'm still going to bring down this x and then down below. The only difference is I'm going to keep the e part here. So write this as the limit as x goes to infinity of e to the x times natural log of 1 minus 2 over x. And then I'm going to write that as the limit as x goes to infinity. I'm going to bring that x down below, write it as e to the natural log of 1 minus 2 over x over 1 over x. It's not required, but a lot of people like to put this limit up in the exponent. So the limit of e to a thing is equal to e to the limit of that thing. So we can write this as e to the limit as x goes to infinity of all of that. Natural log of 1 minus 2 over x over 1 over x. Hopefully you guys see how this is the same, right? It's just in this one, I just did the exponent on its own, and then so my answer was e to that exponent. This one, I'm writing e to the exponent the whole way and just taking the limit of it. Same work either way. So now we're going to use Lupital's rule. We're going to get e to the limit as x goes to infinity of, so again, derivative of the top, derivative of the bottom. The derivative of 1 over x is negative 1 over x squared. Put some brackets around this grossness. And the derivative of natural log of some stuff is 1 over the stuff, so 1 over 1 minus 2 over x, times the derivative of the stuff. And the derivative of negative 2 over x was positive 2 over x squared. Again, the x squareds cancel. Two divided by negative 1 is negative 2. So this ends up looking like e to the limit x goes to infinity of negative 2 over 1 minus 2 over x. In this case, the 2 over, let's put some brackets around that. The 2 over x goes to 0, because 2 over infinity gets infinitesimally small. And then negative 2 over 1 minus 0 is e to the negative 2 over 1, which is negative 2. So that's our answer in this problem. Really, we could have done, right? We could have really just, if we wanted to, said, okay, well, just sub in a 0 for infinity here and see that this is going to be negative 2 over 1 minus 0, which will give you negative 2, and then you get e to the negative 2. Same work, just written slightly different ways. So, interestingly, this one, I should have said, right? This indeterminate form here is a 1 to the infinity, right? The base is getting closer and closer to 1. The power is getting larger and larger and larger. So let's talk about the various indeterminate forms. And then we'll do a couple more examples, and then we'll do some optimization. So hopefully everyone's familiar with these indeterminate forms. Indeterminate forms. Wow. So of course we have the infinity over infinity and 0 over 0. Right? Those are the ones that don't require any work. We don't have to manipulate them to be able to use Lupital's rule. And then we have your infinity minus infinities and your infinity times 0. These are also indeterminate forms. Typically, this one requires dividing by one of the things. So, like, for example, if you have the limit as x goes to infinity of, oh gosh, I had an example, now it's gone from my brain. Let's do the limit as x goes to 0 from the right of x squared times natural log of x. That's going to 0. And the natural log of x as x goes to 0 goes to negative infinity. And you should be aware, right? When I say infinity, it really means if the sign doesn't matter, it could be a negative infinity. So infinity times 0 or a negative infinity would also be fine times 0. Here it does matter, right? They should be the same signs infinity. If you have infinity minus negative infinity, that's just infinity plus infinity, which is infinity. So here we have an indeterminate form. And if you rewrite it, look what happens. You get the natural log of x divided by the reciprocal of this, 1 over x squared. The natural log of x is still going to negative infinity. But now you're 1 over x squared was going to 0. So 1 over x squared is going to 1 over 0, which is infinity. So you took your infinity times negative infinity and made it negative infinity divided by infinity, which is an infinity over infinity form. So that's the whole kind of thought with an infinity times a 0. You basically divide by the reciprocal of one of these. You either make it plus or minus infinity over 1 over 0, which is infinity over infinity, or you make it 0 over the reciprocal of that, which is a 0 over 0. Always works. Well, mostly always works. And then the last three are the exponential forms. You have your 1 to the infinities, your 0 to the zeros, and your infinity to the zeros. Anything that looks like this, all of these require doing the e to the natural log of your stuff so that you can bring down your exponent. Okay. Let's do some more examples. But these, I think, are all the types of indeterminate forms that we typically encounter. Let's look at another infinity times 0. Let's look at, sure, why not? Sorry, I had one. Yeah, that'll work all right. Let's look at the limit as x approaches. I had one written down already that I thought was good. I had forgotten it. That's all right. X approaches 6 for the left of x minus 6 times tangent of pi x over 12. This is similar to a homework problem, but not exactly the same as the one someone asked me about. Oh, I remember what I wanted to change. I just forget. I have a meeting on Monday and I always change my video setting so that you can see my face. But then I forget to turn that off so that now you can see the board better. Hopefully you can see the board slightly better than you could before. All right, so if we plug in 6 here, 6 minus 6 is 0. And if you plug in 6 here, tangent of pi 6 over 12, well, that's tangent of pi over 2, and that is undefined, and it actually is some sort of infinity. If you look at the graph of tangent, so this is the regular graph of just tangent of x. If you look, you have a vertical asymptote at pi over 2 and negative pi over 2. It looks like this. So if we're approaching pi over 2 from the left, which we are, because if we're coming at 6 from a little bit less than 6, if we're a little bit less than 6 pi over 12, we're going to be a little bit less than pi over 2. So if we approach from this side, we're going up to infinity. Although it wouldn't really matter which side, since you'd either have a 0 times infinity, or from this side, a 0 times a negative infinity. Either way, it's indeterminate. Okay, 0 times infinity. What are we going to get this time? Good question. So we need to rewrite this. And the thing is, it's not always really super obvious which thing should come to the denominator as a reciprocal. Typically, the guiding principle is that you want to pick the thing that's going to make it easier to differentiate stuff. So let me show you both your options here. One option would be to write this as the limit as x goes to 6 from the left of x minus 6 divided by the reciprocal of tangent. That seems like it might be gross. Okay. The other option would be to do the limit as x goes to 6 from the left of tangent of pi x over 12 over the reciprocal of that, which is 1 over x minus 6. And so they both look kind of terrible. If you do this one, well, we'll talk about this then. If you did this one, the derivative of tangent and some stuff would be secant square root of this stuff. But the derivative of 1 over x minus 6 squared is going to be, so you're going to have to use the, like, x minus 6 to the negative first would be negative x minus 6 to the negative second. So this one, typically, you don't really want to bring the thing that's just x to a power to the bottom unless it's with a natural log. Like this is the only time when you've got a 0 times infinity where you want to bring the x to the bottom. Because the problem with this here is that when you take the derivative of x to a negative power, this is the limit as x goes to 0 of the natural log of x over x to the negative 2. When you take the derivative of that, you're going to get negative 2x to the negative 3. Essentially, if your power is already negative, your power keeps getting more and more negative when you start taking derivatives. It doesn't end up being a problem here because the derivative of the natural log of x becomes 1 over x. And this problem you can simplify because you just got powers of x over powers of x. But that's not going to be the case over here. Right? I think the derivative of tangent, you're not going to get just powers of x, you're going to get secant squared or something. So this is not the way we want to go. It's not going to get any simpler. Instead, and usually there is one right way to do it and there's usually one wrong way, right? Really honestly, usually you have a choice and usually one choice will work just fine and one choice might never work, probably. It might work, but I feel like it's not gonna. So let's do it this way. And now the thing here is the derivative of 1 over tangent might sound awful until you remember that 1 over tangent is just cotangent. So I can write this as the limit as x goes to 6 from the left, throwing away this pen, of x minus 6 over the 1 over tangent is just cotangent of pi x over 12. And now this might be pretty manageable. Let's use Lupital's rule. So you can see the limit as x approaches 6 from the left. The derivative of x minus 6 is just 1. And the derivative of cotangent of some stuff is negative cosecant squared of that stuff of pi x over 12 times the derivative of that stuff. And the derivative of pi x over 12 is just pi over 12. Okay, now we have to ask, can we just plug in 6 and get an answer? It's a really good question. Interesting. Yeah. I should mention, right? If you plugged in 6 here, you would get 0 over 0. 6 minus 6 is 0. Cotangent to pi over 12 is 0. Okay, what about over here? Sorry, cotangent of pi over 2, not pi over 12. Cotangent of 6 pi over 12 is pi over 2, which is 0. All right, if I plug in 6 here, I have to deal with cosecant of 6 pi over 12, which is cosecant of pi over 2. Anybody know what cosecant of pi over 2 is? Well, it would be problematic if it was 0. Is it 0? There might be a way to make this easier. What's the reciprocal of cosecant? Well, cosecant's 1 over sine. So I can write 1 over cosecant squared as just sine squared of pi x over 12. Still negative. Dividing by pi over 12 is like multiplying by 12 over pi. And now we can just plug in 6. 6 times pi over 12 is pi over 2, and sine of pi over 2 is 1. So this is negative 1 times, or negative 1 squared, which is negative 1. Because it's not negative 1 squared, it's negative 1 squared. It's negative 1. Times 12 over pi. I feel like I lost the minus sign. Oh, I did. I did this problem a little differently than the one that people had for their homework. So I get negative 12 over pi. I think the problem people had in their homework was like this, except they had a 6 minus x instead of an x minus 6, which would change the sign of our final result. But I want to point out, in this particular problem, 0 times infinity ended up equaling negative 12 over pi. Kind of strange. Okay. Weird. Where are we at time-wise? Okay. Let me do 1 or 2 more exponential ones, because I feel like of all the ones, those ones are typically can be very challenging. So let's look at something like the limit as x goes to 0 of, what have I got for you? Sure. Sine of x to the x squared power. That looks like it's going to be terrible. Are there any feelings about which way we do this? Meaning, do you guys prefer that I do it like this, where I write it as e to the, I always forget the limit when I start writing this. It's the limit as x goes to 0, the sine of x, come on, James, of e to the natural log of sine of x to the x squared. So who votes for this? And who votes for me just doing this? Limit as x goes to 0 of natural log of sine of x to the x squared. Does anyone prefer this? Guys, like, we don't care, just do the problem. Yeah, okay. Hearing no opinions from anybody, I prefer the first one. Okay, great. Awesome. Somebody said something. Good stuff. Okay. So we'll do it like this. And again, the whole thing is that once you've done the natural log of your stuff, the power comes down and then comes down below. So I think you can do these next 2 steps really in one step. In fact, I'm going to show you the result and then I'll show you the intermediate step. So the result is you get the limit, holy smokes, as x goes to 0. I should point out, this is not really a big deal, but it should be the limit as x goes to 0 from the right. The reason it needs to be from the right is because if you're approaching 0 from the left, then your power might be negative, and 0 to a negative power is just problematic. So don't sweat it too much, though. It's really not that big a deal. So the 2 steps I'm going to do in 1 are bringing the x squared down in front and then down below the natural log of sine of x as its reciprocal. So this is going to equal e to the natural log of sine of x over x squared brought down below is 1 over x squared. I think it's perfectly fine to do all of that in one step, but if you want to do it in 2 steps, that's also fine. So the intermediate step is bringing this x squared power down in front of the natural log. So this is the limit as x goes to 0 from the right of e to the x squared times the natural log of sine of x. And then the x squared comes down below as the reciprocal. Remember, whenever you're moving something to where it wasn't, it's the reciprocal of what it was. Okay, now we have to use, now we get to use L'Hopital's rule. And so let me check, do we get to use L'Hopital's rule? The answer should always be yes, meaning, and I should back up slightly, if you have an indeterminate form, which this clearly is, sine of 0 is 0, x 0 squared is 0, 0 to the 0 is an indeterminate form. If you have one of these exponential indeterminate forms, if you make the appropriate steps, once you get to this step here, you'll always have an e to the 0 over 0 or infinity over infinity. In this case, it's going to be infinity over infinity because you've got a natural log of 0, which is going to negative infinity, and a 1 over 0, which is going to positive infinity. It's always going to work out. You don't really have to check it if you know you're starting with a 0 to the 0 or infinity to the 0 or 1 to the infinity. Still good to check. Huh, that's interesting. I hadn't thought of that. Okay, that doesn't matter. I'm thinking of some stuff that's like, oh, that's kind of neat. All right, so let's use L'Hopital's rule. And I think it's okay to leave the limit out here, but you can also write it up in the exponent if you want. With the limit, x goes to 0 from the right, of e to the, okay, let's see what happens here. So the natural log of sine of x is 1 over sine times cosine. And the derivative of 1 over x squared is, let's see, that's x to the negative second. The derivative is negative 2 x to the negative third. That's looking bad. I've got cosine over sine, which is going to be undefined because it's 1 over 0. And I've got this too. Okay, so this is a place where you might fall into the trap of trying to just keep doing L'Hopital's rule. It's not going to help. Cosine over sine is cotangent. The derivative of that's not terrible. But this negative 2x to the negative third, its derivatives are just going to have powers that are more and more negative. So this is a place where you have to kind of switch it up. Meaning I'm actually going to put the thing that's on the bottom on the top and the thing that's on the top on the bottom. So let me do one step first. I'm going to write this as the limit as x goes to 0 from the right of e to the, I'm going to say cosine over sine is cotangent. And I'm going to say the denominator is negative 2x to the negative third. And then I bring the x to the negative third to the numerator as x to the third. And the cotangent down below is 1 over cotangent, which is tangent. So let's see what I've got now. I've got the limit as x goes to 0 from the right of e to the, so I'm going to have x to the third on top. I'm going to have a negative 2 tangent x on the bottom. Let me ask you guys, can we use L'Hopital's rule here? Is this exponent a 0 over 0 or infinity over infinity? Well, clearly 0 on top because x is going to 0. Is it 0 on the bottom? Is tangent of 0 equal to 0?
Yes.
Yes.
Yes, probably. Yeah, it's 0. So this is still a 0 over 0 form. So we can use L'Hopital's rule again. You get the limit as x goes to 0 from the right of e to the, let's see, the derivative of x cubed is 3x squared. The derivative of negative 2 tangent is negative 2 times secant squared. And I suppose, so I'm going to say something here, then I should back up a little bit because I didn't do something I should have done, kind of. So every time, and this is what I mean, so every time we use L'Hopital's rule, we should always check to see if we can plug in our limit. So x is approaching 0, I get 3 times 0, that's 0, and secant of 0 is 1. 0 over negative 2 times 1 is just 0. So this is e to the 0, which is 1. The thing I was saying I should have done that I didn't really do was technically, right when I went from here to here, I used L'Hopital's rule. I should have checked to see if I could just plug in 0. I couldn't, right? I mean, I guess I kind of did. Like, there's a little hand wavy about it. If I plug in 0 here, right, I get cosine of 0 over sine of 0, which is 1 over 0, some sort of infinity. And the denominator is also some sort of infinity. So it's definitely still indeterminate. So yeah, these can be a bit of work. But again, the steps are kind of always the same to start. You're always taking the e to the natural log of the thing. You are then bringing down the power and then bringing down that coefficient. And then you're using L'Hopital's rule. Excuse me. Should we do one more?
Yes, please.
Okay. Let's do another one of this type. Let me see if I've got, let's see, we did a 1 to the infinity, we did. Let's see if I've got an infinity to the 0 laying around anywhere. Sorry, one sec. Do I have an infinity to that's not the one I want to look at. You're dumb. So not you guys. The problem I'm looking at is not my favorite. That's a good one. Sure. Let's look at this problem. This one's not an infinity to the 0, but that's fine. So let's look at this one. Let's look at the limit as x approaches 0 from the right of e to the x plus x to the 1 over x. And again, or not again. Let's see. So let's talk about what this is doing. E to the 0 is 1 plus 0. And 1 over 0 from the right is some sort of infinity. So this is a 1 to the infinity. And it's definitely an indeterminate form. So let's do the whole process. This is going to be the limit as x goes to 0 from the right with e to the natural log of e to the x plus x to the 1 over x. So this time I'm going to put the limit in the exponent just to see how that looks. So I'm going to write this as e to the limit as x goes to 0 from the right I'm going to bring down the power in front of the natural log. So it's going to be 1 over x times the natural log of e to the x plus x. Notice, if you care, that now this 1 to the infinity has become, well, that's still infinity times natural log of 1. Natural log of 1 is 0, so this is an infinity times a 0 form. Okay. In this problem, you don't really have to bring the x to the denominator because it's already kind of in the denominator. If you really wanted to, you could write it as e to the limit as x goes to 0 from the right of the natural log of e to the x plus x over the reciprocal of 1 over x, which is x over 1. It feels kind of silly to write x over 1 though, when I could just write x. And really, you can just kind of see, oh yeah, look, I already kind of have natural log of e to the x plus x over x. And now I have a 0 over 0 form. Denominator is 0, numerator is the natural log of 1 plus 0, natural log of 1 is 0. All right. So, oh my God. Sorry, someone in my work chat just sent everybody the Mario Lopez Lifetime Special, A Recipe for Seduction ad, which, if you haven't seen it, is kind of hilarious. I was hoping I could just throw it in the chat there because it's kind of worth seeing. But oh yeah, maybe go. Maybe you can click on that. I have no idea. Maybe not. I don't think so. Too bad. Well, you should go look at that. However you want to find it. It's kind of hilarious. All right, sorry. Back to the math. So we're going to use Lupital's rule. We're going to e to the limit as x goes to 0 from the right of derivative of the top. Okay, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of e to the x plus x is e to the x plus 1 over the derivative of the bottom, which is just 1. And now I think we can just plug in, or at least we should check, right? Even if I think we can't, we should still check. So if I plug in 0, I get e to the 1 over 1 plus 0 times 1 plus 1. So I get e squared. Interesting. So those are some examples of L'Hopital's rule exponential forms. And it's definitely something I would imagine would be on whatever sort of final test you have. All right, let's do a few optimization problems, because I know people had questions about optimization. Let's see. Someone sent me a question that I'm going to repurpose just a little bit. That was a good question. Let me grab it here. That is not exactly, okay, that's fine. Sure. So I want to, that's a slightly different problem. Let me think for a second how I could write that. Sorry, 1 sec. Let me just think for 1 minute here. That's kind of weird. Okay. Yeah, that's dumb. Okay. So let's say we've got this. Let's say I want to find the dimensions of the largest rectangle with a diagonal of length, let's go with 8. All right, so I want to find the dimensions of the largest rectangle by area with a diagonal of length 8. There's my rectangle. There's its length. So its length of the diagonal is 8. And I'm trying to maximize the area. So I need an equation for the area, which means I need to label the sides. I don't know any side lengths, so all I know is the diagonal length there. So So I'm going to call this side x. I'm not going to call this side y. I mean, you could, but I'm just going to go ahead and do the work and figure out what this side has to be. So I know via the Pythagorean theorem, I told you I'm going to call it y for just a second. Okay, fine, it's y. I know that x squared plus y squared equals 8 squared. So that y squared equals 64 minus x squared. And that y is the square root of 64 minus x squared. Speaking of the square root of 64 minus x squared, did Karan ever post solutions to that paper folding problem? If she did, I would love to see them because it was a hard problem. Anyway, back to this. So my area equation, or my area as a function of x. Okay, well, if she does post them, send me an email with them because I would really love it because I had spent too much time working on that problem. It was interesting. So the area here is going to be x times the square root of 64 minus x squared. And we want to minimize the area. Sorry, maximize the area. Yeah, I'm going to talk about the other way we can do this as well. But let's do it this way first. So we're going to take the derivative. I'm going to think of this as x times 64 minus x squared to the 1/2 power. Use the product rule. It's 1 times 64 minus x squared to the 1/2 plus x times the derivative of 64 minus x squared to the 1/2, which is going to be 1/2 times 64 minus x squared to the negative 1/2 times negative 2x. And this is kind of always gross to solve. I mean, it's not like the worst thing ever, but it's not particularly nice. It's still manageable. Let's see what we get. That's an interesting thought that I just had. So I'm going to factor out as much as I can. I'm going to factor out a 64 minus x squared to the negative 1/2. So I do that. I'm left with a 64 minus x squared to the positive 1 here. Because if you multiply this by this, you would add the powers, and negative 1/2 plus 1 would give you back the 1/2 power you had there. And then here I'm left with an x times a 1/2 times a negative 2x, which ends up being a minus x squared. So simplifying, this is 64 minus x squared, which is 64 minus 2x squared, divided by, well, this is 64 minus x squared to the negative 1/2, so it comes to the denominator. It's 64 minus x squared to the positive 1/2, which is the square root of 64 minus x squared. If we set that equal to 0, we get 64 minus 2x squared equal to 0. 64 equals 2x squared. X squared equals 32. So x is the square root of 32. Okay. So now, before we find y, we have to answer the other question, which hasn't been stated, which does this actually maximize the area? To answer that, we really should talk about the domain of area equal to x times the square root of 64 minus x squared. What's the smallest x can be here? Well, there's two right answers to this question. One right answer would be negative 8. If x is negative 8, you get 64 minus 64, which is 0. Negative 8 times 0 is 0. But x couldn't be any more negative, right? If x is negative 9, you have 64 minus 81, and then you have a square root of a negative, which isn't real. The issue is, if you look at the picture of what we're doing, it doesn't make sense for x to be negative at all, or even 0, right? Technically, if x was 0, you couldn't have a rectangle with any diagonal length of 8. So really, for this problem, x has to be bigger than 0. And for this problem, x really has to be less than 8. Because y has to also be bigger than 0. And y is the square root of 64 minus x squared, which means x has to be less than 8. So this is our domain that we're working with. So if we're on the number line from just 0 to 8, and I have my one critical point, which is the square root of 32, which I know is between 5 and 6, I want to make sure that this actually is a maximum. Let's pick a number less than square root of 32. I'm going to pick 1, plug it into the derivative. Ooh, okay. So here's my derivative, simplified. I plug in 1, the top is 64 minus 2. The bottom is the square root of 64 minus 1. So positive over positive, which is positive. Nah, come on. Okay, pick something bigger than the square root of 32. I'm going to pick 7 because I'm sure it's bigger. It's less than 8. I pick 7. 64 minus 2 times 49 is negative, and the square root of 64 minus 49 is positive, and negative over positive is negative. So my function is increasing, decreasing, so yes, we do have a maximum at the square root of 32. So yes, x equal to the square root of 32 maximizes the area. And then we still need to find y. So here's my equation for y. So that I plug in the square root of 32 for x, I get y equal to the square root of 64 minus the square root of 32 squared. But that's just the square root of 64 minus 32, which is just the square root of 32. So x and y end up being the same. Looks kind of neat. I would say it's kind of typical, right? Often when you're doing anything with a rectangle, you frequently get your answer to really be a rectangle where the base and the height are the same length, so you get a square. That is often going to be the case. I'm not going to do it, but I do want to mention that alternatively, you could have solved this. Yeah, I said I'm not going to do it. I'm probably going to do it. You could have solved this instead by using trigonometry. You could have said, okay, got a rectangle here. Diagonal is 8. Sorry, yeah, diagonal is 8. This is y, this is x. Area is x times y. Instead of writing x in terms of y or y in terms of x, you can say, okay, well, this angle, I can say that the sine of that angle is y over 8. I can say the cosine of that angle is x over 8. So that y equals 8 times sine of theta, and x equals 8 times cosine of theta. And then you can plug those into your equation and say the area as a function of theta is 8 sine theta times 8 cosine theta. Which isn't terrible. Then you can take the derivative. The derivative of 8 cosine theta is negative 8 sine theta times 8 sine theta plus 8 cosine theta times the derivative of 8 sine theta, which is 8 cosine theta. And then if you set that equal to 0, you can factor out as 64 times cosine squared minus sine squared. And you'll be like, oh, well, sine has to equal cosine. And we know the angle where sine equals cosine is pi over 4. So this angle ends up being pi over 4, which means x and y are the same. And you get y equal to 8 sine of pi over 4, which is 8 times root 2 over 2, which is 4 root 2, also known as the square root of 32. And x is the same. So that's another way you can do a problem like this. And often the arithmetic, the algebra is just a little bit easier when you use an angle like this. I'm not saying you have to do this, I'm just saying it can be nicer this way. Let's look at some other examples. Some other optimization problems. Where'd you go? Oh, I had one. Let's do this one. That's a good one. I want to find the point on the parabola y equal to x squared closest to, closest to 0, 1. So when we hear the words, find the point that's closest to on a thing that's closest to another point, the thing we should be thinking is we're trying to minimize the distance between the graph and the point. Let's draw the graph. Y equals x squared looks like that. And here's the point 0, 1. So we're trying to find some point on this function where this distance is minimized. So we want to minimize distance. And we know that this point is 0, 1. And we don't know what the red point is. We just know it's some point on the graph. So that's the point x, comma, y. Or if you prefer, since we know we're on the graph y equals x squared, it's x, comma, x squared. So I want to write an equation for distance. Distance is equal to the square root of the difference in the x's squared plus the difference in the y squared. So it's going to be x minus 0 quantity squared plus x squared minus 1 quantity squared. Which we can simplify. So I've got the distance is equal to the square root of x squared plus x squared minus 1 squared. Okay, there are two different directions we can go here that both have the same result. In fact, let me show you how they have the same result. So one way is just to take the derivative and set it equal to 0. So I've got some stuff to the 1/2 power. My derivative is going to be 1/2 times my stuff. Let's write this over here. Derivative is going to be 1/2 times my stuff, which is x squared plus x squared minus 1 squared to the negative 1/2 times the derivative of the inside, which is 2x plus 2 times x squared minus 1 times 2x. And I'm going to simplify this just a tiny bit. I'm going to bring this down to the denominator. So I'm going to write this as this numerator, which I'm not going to change, 2x plus 2 times x squared minus 1 times 2x over 2 times the square root of x squared plus x squared minus 1 squared. And we're going to set this equal to 0 and solve. But I want to point out, there is a thing we can do that's going to make this way easier. Instead of doing this, it is just as, what's what I'm looking for? It is just as correct, it's equivalent to minimize the square of the distance. So the distance squared is equal to just the insides, which is x squared plus x squared minus 1 squared. If I take the derivative of that, I get 2x plus 2 times x squared minus 1 to the first times the derivative inside, which is 2x. Now look, this thing here is exactly the numerator of that there. And if I'm solving this equal to 0, it'll be the same as solving this equal to 0. Additionally, I don't have to worry about missing any critical values from here, because this derivative will never be undefined because this denominator can never be 0. And it can't ever be 0 because that square root is that square root, which is the distance between this point on the graph and this point not on the graph. And that distance can never be 0 because that point isn't on the graph. So you can do it this way, but it feels like it's going to be a bit easier to just do it this way. I mean, really, it's the same amount of work, but writing this derivative just feels kind of less nice. Are there questions about this particular thing before we go on? So if you ever have to find the point closest, instead of minimizing the distance, minimize the square of the distance because it's going to be easier. Okay, I'm going to solve this equal to 0, and I'm going to do that by factoring out a 2x. So I get 2x times 1 plus, I'm factoring out that 2x, I'm left with 2 times x squared minus 1. So let's take 2x times 1 plus 2x squared minus 2. So I get 2x times 2x squared plus 1 minus 2 is minus 1. All right, I'm going to erase all this since I don't really need it. So I either get 2x equal to 0, which is going to give me x equal to 0, or I get 2x squared minus 1 equal to 0, which is going to give me 2x squared equal to 1, x squared equal to 1/2, x equal to plus or minus the square root of 1/2. So unlike most of our examples, we actually have more than one candidate for what's closest. It could be the point 0, 0, or it could be the point, let's see, well, there's actually 2 points, right? There's x is the positive square root of 1/2, and y is x squared, and the square root of something squared is just 1/2. Or it could be the one over here. It could be negative square root of 1/2, comma 1/2. And I should note that by the symmetry of this graph, this point and this point are equidistant from the point 0, 1. So you're either going to get 0, 0 being the closest, or these points are both the closest points. We have to check. So we actually have to use, so you could either, this is a good, you could either use the first derivative test, we can use the first derivative test. We can also use the second derivative test. We'll talk about it in a second. So using the first derivative test, pick a number larger than the square root of 1/2. Go big. Pick 1,000. 2 times 1,000 is positive. 2 times 1,000 squared minus 1 is also positive. Positive, positive, positive. Now it's a little bit harder to pick something that's between 0 and the square root of 1/2. Because the square root of 1/2 is like, I don't know. Square root of 1/2 is, it's like 0.707. Right? Square roots, when you take square roots of numbers that are large, smaller than 1, they actually get bigger. Kind of interesting. So the square root of 1/2 is like 0.7. Pick something smaller than 0.7. Let's just pick like 0.1. 2 times 0.1 is positive. 2 times 0.1 squared is pretty small, and the pretty small number minus 1 is negative. So positive over negative is going to be a negative. Same deal over here, except now I'm picking a small negative number. So this part's negative and this part's negative, which makes it positive. And then over here, pick negative 1,000, negative, positive, all things negative. So our function, our distance squared, is getting smaller, then getting bigger, then getting smaller, and then getting bigger. So right here and right here, the square of the distance is as small as possible. Right here, the square of the distance is actually not as big as possible, but bigger than anything around it. So it's kind of interesting. If you travel like from left to right, so here we're really far away, and then we get closer, or we get closer, 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 closest. And then from here to here, we actually get a little bit further away. Right? All those points, these points are further away, furthest away in this region. Closer, closer, closest, further away, further away, further away, further away, further away. So it's kind of a neat problem in that, oh yeah, there are 2 points that are closest. So my points that are closest are in fact the points negative root 1/2, comma 1/2, and positive root 1/2, comma 1/2. If you prefer, well, actually, I don't know. We could try to use the second derivative test. Let's see if it works. So again, if I hadn't done the distance squared, I definitely wouldn't try using the second derivative test because that would be awful, right? If I was taking, right, remember the derivative I had over here, if I was taking the second derivative, that would be not fun. But taking the derivative of this is not so bad. So let's actually look at this. So here's my function, my d squared prime. I'm going to multiply this out and get 2x times 2x squared is 4x cubed minus 2x. And then plug in, and then take the derivative of that. You get 12x squared minus 2. And we can see that if you plug in to d squared double prime of 0, if you plug in 0, you get negative 2, which means it's concave down, which means it's a max. We're looking for a min. If you plug in, d squared double prime of 1 over the square root of 2, the square root of 1/2. Sorry, I know it's a little messy. A square root of 1/2 squared is 1/2. 12 times 1/2 is 6. 6 minus 2 is 4. That's positive, which means it's concave up, which means we have a minimum. So yeah, that would also work. We have a minimum here, and by symmetry, we also have a minimum there. Cool. There was something that was rolling around in my brain. I don't know. Let me see. Let's do one thing, but let me grab all your names here while I'm thinking about it. So many of you. Okay. Let's see. Do I have another good problem? Oh, do I have a 5-minute problem? I'm sure I have it on this other page here. Sorry. Sure. Here is a. Oh, I was thinking about a problem I could have come up with this morning, but yeah. Oh well, I'll say that for next time. So let's look at this problem, which I guess is number 53 in section 4.3. If the rate of flow from blood to the organs is alpha. So rate of flow of blood from the organs, to the organs is alpha. And rate of metabolism is from the organs. Sorry, my writing is not always the best. Is beta. Or you use A and B if you don't like writing alpha and beta. Then concentration of a drug under certain conditions is given by, let's just say, at time t, is given by C of t equal to e to the negative alpha t minus e to the negative beta t divided by beta minus alpha. What is the predicted concentration at time t if the values are very close to each other? So if a alpha and beta are close to each other, what do we expect So this is a kind of roundabout way of asking you a limit question. Because if you just say beta and alpha are equal to each other, you get e to the negative alpha t minus e to the negative alpha t, right? They're equal to each other over alpha minus alpha. That's going to be a 0 over 0. So this question, right? This question, phrased kind of oddly, is really asking, what's the limit as alpha approaches beta of this expression? seems a little bit weird, but we can use Lupital. So it's really kind of interesting here. What's the constants? Or I should really ask, what's the variable? And I know people probably want to say t is the variable. In this particular setup, t is not the variable that we're interested in. In this particular setup, alpha is actually the variable. Because I'm talking about how alpha is changing. Alpha is approaching beta. So it's really, really important to read the questions very carefully so that we can kind of decide, all right, what are we really thinking of as the variable? What's the constant? Most of the time, you're like, oh, t is the variable. In this case, it's actually alpha. And everything else, beta and t, are constants. So I'm going to use L'Hopital's rule. The derivative e to the negative alpha t is going to be e to the negative alpha t times the derivative of negative alpha t, which is going to be negative t, because it's the derivative of your variable times the constant that's left over. Weird. Minus the derivative of e to the negative beta t. There's no alphas in there, so its derivative is 0. Over the derivative of beta is 0. The derivative of negative alpha is negative 1. So this ends up equaling, and now I can plug in alpha or beta. It doesn't really matter which way I want to do it. If I plug in, I guess I should plug in beta. I'm going to get negatives cancel, so I get t e to the negative alpha t, or negative beta t, sorry. Again, it shouldn't really matter since alpha and beta are supposed to be the same. Kind of a strange question. So as the rates approach each other, right, as the rate of metabolism is approximately equal to the rate of concentration of blood, or the rate of flow of blood, sorry, then the concentration, as those two things get closer and closer to each other, the concentration of the drug gets closer and closer to this particular value. It's kind of a strange question.